Hi, everyone. So welcome to the second part of our workshop, and it's my pleasure to introduce the Technical Outreach Manager for the National Deep Inference for Arabic, Emma Forts. Emma, I've known Emma now have I worked with you for a couple years now as part of, um, has it been that long?
I
Um,
guess.
yeah,
Since
so,
2024.
but I was introduced to NDIF a couple years ago, and Emma can tell you more about NDIF, and I've already kind of given a bit of a preview in the previous hour. But when we talk about interpretability and providing real computational tools for making that happen and articulating that to interdisciplinary agendas, I think NDIF is just a fascinating endeavor and an institution. And so, without further ado, I'll turn things over to Emma to conduct our interpretability workshop for the rest of the morning. Emma, welcome.
Hi, everyone. Okay. Um, Thank you so much for having us. We're really excited to present the NDIF project and just talk to you about AI interpretability a little more. So I'm Emma Bortz. I'm the Outreach and Education Manager for the NDIF team. Also on the call are Adam Belfke, who's one of our research engineers, and Gwendolyn Croft, who's a PhD student working on the project. So, the way that this next 2 hours will be structured is that we'll go over some background, probably retouch on some of these AI model basics that you discussed with Michael in the last hour, and then go over the NDIF project and what our mission is. Then the bulk of the work will be spent in an interactive demo session where we'll be working on two of our user interfaces for interpretability techniques called Logit Lens and causal mediation. And then we'll have a reflection period, and we'd love if you could participate in a feedback survey so we can improve this workshop in the future. Um, we'll be using Slido for some interactivity throughout the workshop. So you can join on your phone or on your browser by just going to slido.com and entering this code. And on all the Slido slides, this will show up. So no need to set it up now if you don't have time. Great. So first off, we're going to talk about an AI background, specifically about AI models. So our first Slido, I'm curious to learn what types of AI models you can name. Um, and I'd be really interested to learn if there are any that are specific to sustainability that you can think of. So I'll pause here for a second and uh, just enter as many as you can think, and it'll create a word cloud. Oh, we got two gemmas. Very popular. Um, okay, this is super cool. So, you guys seem like you're familiar with language models and some other types of machine learning models and neural networks. Okay, so we're gonna move on. I've just one second. Um, Created like a really bit broad overview of different types of AI models that you might be familiar with. So there are supervised machine learning algorithms that can be used to create classifiers or clustering. There are neural networks that are unsupervised and have hidden states that the networks can learn themselves. And then I don't think anyone mentioned image generation back there. So there are also these image generation models that operate through a diffusion process to create images. And then text generation is what this workshop is going to be focused on. So that's your Claude, that's your Gemma, um, that's your Chat GPT. Text generation models take a text input, put it through a LLM, which we'll talk about on the next slide, and then we get a text output. And then there are also domain-specific models in AI companies. So there's AlphaFold for protein biology. There's Open Evidence for healthcare workers. And then I looked up sustainability AI models slash companies, and I found these two. No idea if they're um, open source or not, but thought I'd share those there. So large language models are essentially next word generators at the simplest level. So you have your input for here, it's once upon, and then it goes through the LLM block and outputs one more word. And then to get a long generation of text, they just string that next word onto the input, and you can keep on putting it through to get a long string of text. Inside of these models are blocks called transformer blocks. So the way that data is processed as it moves through the model is that first the input prompt is tokenized. So it goes from Miles Davis plays thee to Miles Davis plays thee. Then the encoder block of the model turns each token into a vector of what are called neural activations. And these neural activations then flow through the network through a series of transformations that mixes each of the tokens and then the layers progressively. So we'll talk a lot about these layers of the models. So it's an important concept to understand is that as the data flows through the model, the prediction is progressively refined. And then you have the decoder module once you reach the end of the layers that can turn each of these vectors into a prediction for the next word. So we'll talk about how that works. So for this prompt, the predicted guess is trumpet. And then you also, it's important to know that because this is a grid and the operations are happening for each token, there's also a guess for just when you put miles into the network. One detail about what these guesses are that they are probabilities throughout the model vocabulary. So trumpet here has the highest probability out of all the other tokens in the vocabulary. So it's what the model ultimately selects. Cool. So let's go into this in a little more detail. Tokenization and encoding is the first step. So you have a text prompt. The Eiffel Tower is located in the city of blank. So the way that this gets input into the model is it gets turned into tokens first. So you go from your string of words to tokens. Tokens can be representative of one single word or parts of a word or different characters. So you can see Eiffel is actually split into multiple tokens here. Tokens are all representative of a specific ID within the full model vocabulary. So they will all have a specific ID number. And then what the encoder does is it just takes these IDs and creates a vector that matches the dimensions of the neural network so that the processes can go throughout these layers. And it uses something called an embedding matrix, but I think that's getting a little too complex for our purposes. So the key thing to know, there are two key things to know for this, for understanding our demos, and it will be tokenization, and the second thing is the residual stream. So the residual stream is how information flows throughout the layers of the model. So every layer has an input and an output. And we can actually take this output and study it and perform different operations on it to take it as a sort of proxy of where the model's state is at that point in its computations. So every layer calculates this residual vector, and it adds it to the stream. And that is why we call this the residual stream. So we'll talk a little bit more about residual stream once we get into the specific techniques that we'll be covering. And then finally, after the operations take the information flow all the way through the layers to the end of the network, um, these the final layer collects raw scores for each token in the vocabulary. These are called logits. And then an operation called softmax transforms the raw logits into probabilities. So over the whole vocabulary, it will say, okay, there's a 90% chance the next word would be trumpet, a 9% chance the next word would be horn, and then maybe a 1% chance of everything else. So the model will say, okay, 90%, I like that. I'm going to output trumpet. So that is how the information flows from prompt to output. I think that was probably an overview and maybe a repeat of what Michael presented last hour, but if anyone has any questions there, feel free to chime in.
And I think it's great to have a couple of coats of paint here.
Yeah, awesome. Okay, cool. So now you may be wondering, what is NDIF? NDIF, as Michael mentioned, is the National Deep Inference Fabric. So our goal is to move beyond black box AI. So most of the models that you have interacted with are probably black box. So this is your typical like ChatGPT interaction where if you're an end user, like this doctor, you might ask the model, I have this patient, they're in pain, should I prescribe codeine? And the model will give you a text response. No, don't prescribe codeine. However, NDIF's goal is to empower scientists and researchers to ask, why did the model output no? So at a high level, the way this works is you can make a request to our API that says the prompt, prescribe codeine. But it also, you can ask to return rich information from within the model as the computations are flowing throughout that network. So you can ask to return, for example, the activations at every layer in the residual stream. And you could ask to return the output probability distribution. And then instead of just getting the answer no, you get a rich model response that you can use for further research. I see something in the chat, just making sure. Okay, great. So NDIF is an NSF-funded project to make AI interpretability research accessible to all. So our goal is to eventually allow scientists to probe and alter internals of enterprise-level models that are on the scale of trillion parameters, like the Claudes and ChatGPTs of the world. Unfortunately, those models are currently closed source, so they will not allow us to even know what is inside of them. But we're starting with open source models. So to do this, we have a software called Nsight that is a unique, transparent AI inference library. And we also have created different user interfaces and other software libraries that are built around this core Nsight library. We also have capacity. So the NSF has provided us with GPU hours so that we can actually host AI models for you on what would cost millions of dollars worth of resources, which is just inaccessible for an individual research lab. We also have a focus on education and interdisciplinary training on these enabled AI methods. So that's part of why we're building out these workshops is to move this AI interpretability research and get all the greatest brains in the world working on it and not just limit it to those in computer science. So a little bit about our ecosystem. Starting from the more technical side, so we have our server. This is where we host the LLMs on GPUs. And we have a hot swapping system in place so you can swap in different niche models from Hugging Face, which is a website that stores the weights of different open source models. And so we serve these for free for research use. Moving forward, we have Nsight, which interfaces with our server via remote access. And then it also includes primitives to allow you to define interventions on these models. So it's a Python library. It's written, built on PyTorch. So if you're familiar with PyTorch, it can access the models in a very similar way. And it works with not just language models, but any PyTorch model. We've also recently added skills for AI assistance with the increased prevalence of coding models. So these skills will hopefully help coding models use Nsight and create research experiments without needing to be an expert in the library. Moving to a higher level, we have the NNTerp library. So it's a standardized and efficient interpretability toolkit built on Nsight. We have a low-level API that includes uniform model naming and different shortcuts. And then we have a high-level API that includes built-in functions to implement popular interpretability methods. So we're very excited about this. It was built by a member of our community and not by our direct team. And we have since brought it into our ecosystem officially. We are also working on this interchange format that enables compatibility between third-party services like these auditing companies and packages. And then it also includes integration for our user interface Workbench. So Workbench is the key focus of this workshop today. It's our no-code user interface that enables discovery and experimentation. And we're very excited. We've implemented some interpretability techniques in it, and we hope to grow it to many more different techniques. So yeah, with that, I will move the slides to Adam, who is one of our engineers and the creator of the Workbench.
All right, so I'm gonna take over here from the great introduction that Emma did and the primer on LLMs. And the first tool I'm excited to show you today is called Logit Lens. But first, I just want to start by asking.
I'll just ask a clarifying question. When you say, do you think LLMs are a black box? Do you mean, do we feel like people treat them like black boxes, or do we believe in our heart of hearts that these are black box technologies that we're more than happy to move along in our lives without ever understanding what's inside of them? Or
More like
something
yeah,
possible?
more about the latter. Like, do you think we understand how these models work the way they do, or do you think that we're still like a long way towards developing that understanding and being able to not just understand how they work, but also be able to control them however we want?
Okay, great, thank you.
Adam, I think you should have screen control now. So
Can people also see my cursor on the screen?
It looks like it, yes.
It is? Okay, awesome. Pretty strong consensus there, I guess. Uh,
Well, if understanding LLMs at every level is like climbing a mountain, I feel like every time there's a primer on transformers, the mountain gets taller and taller in real time. Uh, so I think that supports your case about the black box.
so you feel like the more you learn about transformers, the more you learn about how much you don't know? Is that
Yeah,
what you're asking?
for my sense, the amount of nonlinearity in the behavior of the system or potential nonlinearity in the behavior of the system um, gives me great pause. And so that's why I checked black box yes. Although I see that a lot of people are now going over to maybe. But anyway, that's my 2 cents over.
I would love to hear from the people that say maybe or no why they think LLMs are not so much of a black box. That they think they may be just like memorizing parrots, and that's why they're confident in their answer. I'd love to hear from people. Anybody wants to jump in?
Well, I answered no. I mean, I took the question literally as a, like I know that. So maybe I'm not understanding what you mean by a black box. I think there's a lot
Um,
more to it than just something going in and doing some magic and coming back out again.
right, it's definitely not magic. However, how good it is these days, it feels sometimes that way. Um, but I guess yeah, so I guess we can move on to the next line. I'll try to understand to answer your question. Is this going to work? Look at this. Okay. No, I think I moved to I'm trying to get to the black box slide. If it's not letting me okay.
And I feel like I have 2 microphones in this room, and so I reflexively unmute myself whenever I speak, and that's causing all kinds of problems. What I will say, Adam, like one possible to anchor it in an example would be if we were to ask a large language model to make a prediction about what South Florida would look like with 3 degrees C of global warming, right? So that is a question we could ask a large language model, and we would get some sort of answer. Would we understand how it got that answer? Yes or no? Feels like grounding your question in an example, I think that people might vibe with.
Right. Yeah, that's actually a really good point. And I really like your example. And I guess related to that is, yeah, so it would give us an answer that could be right or could be wrong, but we don't have definitive ways of like determining the underlying computation that resulted in that answer. And actually this is good because the example I'm sort of like want to motivate here is sort of like related to this like geospatial awareness. And I would argue that LLMs are still pretty much a black box and will still have a long way towards fully understanding how they work under the hood and be able to control them. However, NDIF and all the research going on in the interpretability and AI safety space, I think is really critical, and we're making great advancements. So if you were to prompt a small model as GPT-2, which is really tiny and like not at all state of the art, the Eiffel Tower is located in the city. It is going to correctly predict and generate the next token as Paris. But the question comes up as, did the model just simply learn and memorize this fact during training? And so it is just spitting it out because it saw Eiffel Tower, or did it actually develop a geographical representation of the relationships between location entities under the hood? And that is a mechanism that is basically using to output Paris. Uh, next slide. Sweet. So it turns out researchers have developed methods that allow us to look into these intermediate computations to try to answer this kind of questions. So if we look at the top predictions at the different layers of the model, and this is possible using the residual stream architecture that Emma was explaining earlier, we can see that at the earlier layers, the model is sort of just like thinking about some random token. And then as it progresses, it starts thinking about location entities like England. And the further you go, it doesn't just start thinking directly about Paris, but it starts thinking about capital cities, which is really interesting and related to Paris. So it starts with Rome and then London and then Paris, and you can see how like the rank of these predictions sort of rises to the top at the last layers for Paris to finally take over at the end. And so the fact that these intermediate predictions are not random, Paris, it was not just like some gibberish and then Paris just comes up at the very end. There was some logic behind it. Sort of indicates that there is some mechanism that we should be studying under the hood to understand how this prediction worked. And in practice, how does Logit Lens allow us to do this? So what we do is we basically cheat a little bit. And we're going to take the output of a layer at any intermediate layer, and we're going to act like if that was the final layer. And so instead of letting the model continue to run, we take this output at this layer, and we directly feed it into this last decoder module, which basically projects back this dimensional vector into the probability distribution over the tokens of the vocabulary of the model. And like I mentioned before, this is really nice because of the residual block architecture, so that like the dimensions are preserved and the input and the output is also like the same. So if we do that over the previous last layer, second last layer, we can still see trumpet. And so the model became confident in that final answer earlier than the last layer. And if we do that over all the layers, which is the typical thing to do with Logit Lens, we can see that at the beginning, the model is just like attending to names and then attending to the same name in the prompt, and then starts like predicting horn to another instrument, and then finally trumpet. So this is a good place here to now like introduce our user interface where we can, play around with more examples and try to do Logit Lens with just a few clicks. So what I invite you all to do is go to workbench.ndif.us, sign in with a Google account or a GitHub, and then try to follow along with me as I walk you through some interesting examples that might even create some more discussion. Oops, sorry.
May I be a pain for a second and ask a question about reasoning and logic? So it feels like it seems like there is some logic happening, but would we call that capital L logic, or we would just call it some sort of associational process that seems to be like understandable to humans, not necessarily like logic as in like, other schools of AI might call it like formal logic.
So I think that may be an ongoing question in the research field. I think there is different school of thoughts. There are people that are like hard believers that these LLMs have basically like entered the closed circle of thinking, and they're actually doing something really smart, and that humans are not the only entities in our world capable of thinking, and that it's just like, I don't know, just a bunch of like computation. That's all it is. And then others that think that, oh no, this is actually just like some really developed statistical model, and that we will be able to fully reverse engineer it, that it's not that complicated to understand at the end of the day. But I think it's an ongoing question.
All right, thank you so much.
Yeah, of course. And actually the point you raised is very good, because I'm going sort of like at the end of presenting this method, just talk about the limitations of Logit Lens and why you should, once you get preliminary results using this method, you should go and explore more fine-grained methods that try to give you more of like the ground truth information going on there. But this is Logit Lens is always a great start because it's pretty cheap to run and can get you pretty far. Okay.
I stopped sharing my screen, by the way, so
yeah.
you can.
I see a question maybe in the chat. Yeah, really, really good historical background, Jose. Okay. Okay. So I'm assuming everybody reached this point so far. So once you're signed in, you can basically access the very large models deployed on NDIF through Workbench with just a few clicks. What this does under the hood is it will run the same Insight request that Emma explained. And what I like to think of this tool and also of Insight as like a white box API. So if you were to query a model using the OpenAI API, you send an input and you receive the output and even maybe a probably distribution over the tokens. But what this allows you to do is really to grab any intermediate activation, state, computation of the models, control them, edit the model on the fly for your own like experimental purposes. So here, let's go and prompt one of the models on NDIF. I am going to ask it to do, if I can type, a simple translation example from Spanish to Italian for amor. So a few things here happened. So the first thing is the model, the interface is going to tokenize our model, okay, using the model's tokenizer. This may differ from a model to another. So Llama models from the Llama family developed Meta usually has a beginning of text token, which is used for different training purposes. So once this is sent to the remote server, we are going to receive a heat map style table where the x-axis is all the tokens in the prompt, and the y-axis is all the tokens in the prompt, and the x-axis is the layers of the model. And for each cell is going to be the top prediction at that position in the prompt for every layer. And the color scale is the confidence of the model in that prediction, which is just the probability. So we see that the model correctly outputs our expected prediction. For those who speak Italian, I don't, but that would be amore here. And we can sort of see the progression of the probability or like the confidence in this prediction throughout the layers here, which sort of solidifies at the end. But you may also notice that in the intermediate layers at the same token position, we see that love comes up pretty strongly. And this is really interesting because there's no mention of English anywhere in the prompt. There's just Spanish and Italian, and it's still pretty strong. And this is sort of like evidence for a hypothesis in the field that suggests that the models develop a shared representation language. And in this case, the representation shared language is English because of biases in the training corpus for an American model that is mostly trained on English text. And this is really important to understand for people that are either developing models for multilingual purposes or understanding biases or other different like linguistic research directions. I think. So the interface also allows you to view these probabilities over all the layers, which you can also toggle and play with. You can also see not just the top prediction, but also like the other intermediate predictions. So the fact that it's also predicting amor, these are all related to tokenization things. Because models might slice up words in different languages in different forms. I think there's another question. Oh, this is just Emma sharing resources. Sweet. Okay, so this is one example. Let me show you another example from some work that somebody at our lab has been working on recently. So I'm going to paste in here a prompt, and what this prompt does is it assigns numbers to months of the year. And then we're going to ask the model, what month is 5 after 12? So months are sort of like a circle, temporal, I don't know, abstraction or unit. And I'd be really curious to see how the model reasons about this. So it turns out this is not really difficult. It still outputs 5, which makes sense. We can plot its probability. But sort of the interesting thing that the research in our lab has been noticing is that the model may be basically implementing some modulo circuit or mechanism under the hood to be able to solve this task. So the interesting part is that the model's intermediate representations are showing 17 as a top prediction, which is 5 plus 12, but then it still comes to the right final prediction as 5. So this suggests basically some modular mechanism under the hood. And these are the kind of mechanisms that we should really try to understand. And why does the model choose to do this? Like humans might be doing things differently, or there are mechanisms that may be shared between how humans do things and how the models do things because of shared abstractions in the language that we both process. But understanding these kind of things is really key to be able to control, safely deploy these models, or even using them for research in interdisciplinary fields. So now I don't know how much time we still have in this section. Maybe Emma can tell us, but you can play with a few prompts, and then we're still going to have at the end like a exploration section where you can just play more around with the tool and with the prompts.
Yeah, let's do 5 minutes of exploration. We would love if you could share any interesting findings, or if anything's confusing to you, you can ask some questions. And yeah, feel free to try out some sustainability examples, or it's also fun to just change around our prompts, our example prompts, like try out different languages. Looks like there's some stuff in the chat that we can maybe try.
I'm gonna try to read in the meantime Jerry's question. So about the probability distribution, I noticed that when we put in a prompt regarding fact, for example, the EPA regulation for arsenic in drinking water is the actual number tens, probability increases in very late layers, such as layer 70-ish when running Llama 70B. But when I run causal tracing following Enside's paper's methodology, it seems like the earlier layers are more important. Can you explain this a little bit? So by causal tracing, I am assuming you're talking about maybe causal mediation / activation patching, which we'll also cover after this section. But if I were to try to explain your question or come up with an answer, there is a difference between where does the model, I guess, enrich a certain representation at a token level, and when does it get processed at the final token. So it depends on how you set up your causal experiment. If you are patching at an intermediate token, you are going to see that at some earlier layers, this token becomes relevant because that's when its representation gets enriched and it gets processed and flowed through the network to the final token. And then if you patch only at the last layers, that's when you see things emerging way later because it takes time. Sorry, when you patch at the last token, it takes time for that information to flow towards the last token. So it depends on that. And I'm happy to share some literature on that if you'd like to read more on that. It depends on where you're patching. If you're patching at the MLP layers versus the attention layers, you will see different results because of how these modules for each layers interact with each other, and they process information differently and play different roles.
Gotcha. Thank you. I guess I was like running the activation patching by corrupting the subject token. For example, for this one, I corrupted the token for arsenic.
I see.
And then what I realized, like when running the NSX package, what I realized is that mostly it's the first half of the layers that stores the fact related to this kind of arsenic. And I think that's when I read the paper, I think that is what the paper conveys as well. So most of the facts are stored in the first half of the layers in the whole neural network. But then I was like playing with this workbench. When I put it inside and when I say, what's the probability of the 10 showing up because 10 is a correct answer for this prompt, it seems like it only shows up after a very late layers, like a 70 layer 70 or something like that. So I'm just curious, like, why is that? Or maybe like these two, I'm talking about maybe two things differently. Yeah.
No, they are the same. So the probability that you are looking at is at the final token, whereas
Yeah.
the corruption that you're doing is at the earlier tokens. And so these earlier tokens are first like enriching themselves based on their contextual information, because maybe arsenic can have different meanings, right? So like it needs to like enrich its representation in the right meaning. And then at the later layers, the final token will attend to this representation and starts developing a next token prediction. And that usually happens later. So if you corrupt at earlier layers, that makes sense. If you corrupt later, arsenic has already enriched itself, and like it can't recover to predict the right thing. But it's at the final layers that basically the information flows to that last token to predict the right thing.
Gotcha. So in this case, like, can we say like the fact like that kind of connects the EPA regulation for arsenic with 10 ppb, for example, is still mostly stored in the earlier layers.
That's right. That's correct.
Gotcha.
Yes, that's correct.
Yeah, that makes perfect sense. Thank you so much.
And for the audience who may not be familiar with this method, we are going to go over it in this workshop. So, yeah.
Adam, do you want to try running Michael's prompt?
Oh, is there something in the chat?
Right above Jerry's. And then maybe we can run Jerry's too, and then we can move on.
Yeah, this was one where I was looking at a comparison between if I put Northern Alaska and Phoenix, Arizona, and looking at the variation in response between the two.
Is this so okay, I have a comment on Alaska. Okay. So let's just give it you.
Yeah, thank you, Tori. We'll have the recording to everyone who RSVP'd, so you can pick up the back half of the workshop on your own time. Thank you again for attending. Yeah,
So
that's fascinating.
I added new to the prompt, and we are working on extending functionalities that you can generate multiple tokens from like a seeded prompt. Because you may not know exactly if the next thing is going to be the token you're looking for, or is it going to be some intermediate token like new or some like language filling token. But so it does here at least. I'm not sure what information you had that you were expecting, but I guess I see that it like predicts furnace, spoiler, and these are the level of confidence. Let me see. It like thinks of energy in the middle.
Yeah.
As it's processing, I guess sort of like question here.
Yeah, it was using a different model. I was using a 6 billion parameter model, the Luther AI, and it did not make distinctions. It nominated solar for both Alaska and Arizona, which I thought was interesting. And then it's interesting that this model suggests a furnace instead of solar. That is a very interesting set of variations between two models. I think for my part, I would say, oh, just another 2 billion parameters. I wouldn't necessarily bet on it doing a better job of associating place with advice in this way. But in this case, it looks like it has. So I think that's a very interesting result to observe here. I'll just turn it over to the other prompt as well, not to take too much time on this one.
Okay.
And it looks like he did llama 7db.
For Jerry's prompt, yes.
Yeah.
So I need some help reading these sustainability prompts if you think any information is relevant here. But yeah, this is, I guess, sort of the results that I see as pretty interesting. So yeah. So we can also see that the concept of like arson comes up pretty strongly in the middle layers, which is also pretty interesting.
Yeah. And then, yeah, 10, 10, 10. So it comes really, it's quick thinking about arsenic and then converges on 10. So it like finds that fact. But like Adam was saying, this isn't necessarily indicating that these later layers are causally important for determining that fact. And that's why we need to go into our next method.
Mm-hmm. All right. So yeah.
I
Let's
guess, should
move.
I share the screen again?
Yes, please, sure. Thank you.
Slide out. One moment. Okay. You can also see this prompt bank for our next demo as well. Sorry. Present current slide. And then remote control.
So yeah, maybe I can just brush up on this slide, which is related to the discussion I had with Michael earlier about like what does this method actually tell us? And so this method can be limited in the sense that there may be confounding factors related to tokenization, related to decoding some intermediate representation that the model's final decoder module was not trained to properly decode. And so we may not fully see the ground truth there. And people have in the research field have worked on developing more robust techniques that if you're still interested in these kind of like lens methods, you should maybe at some point pursue to try to validate your results or otherwise find that there is another story behind all of that. And so things are like tuned lens, future lens, concept lens, and these usually require some training, requires more data because they like either average over a corpus of like examples to find more like truthful results, or they will like even train some sub networks that are pretty small but like still require some little training. So we just want to make sure that you know how and when to use these methods and their limitations. So next, I will move to causal mediation analysis. And this is we have first a question for you guys. Have you used or heard causal mediation before? Okay, so some people have heard of it or even used it before. And if you have not, that's totally okay because I'm going to try to sort of like explain how it does and more importantly, how is it relevant to understand LLM internals. Let's skip
Why
this
does it
slide.
do that? Do you need any help?
I think I'm just impulsive and I press the key more than once at a time. Okay, yeah, then that one.
There you go.
Okay, so causal mediation analysis is actually a framework that has been used outside of AI and way before, the huge trend of LLMs. And it was first used in epidemiology to understand cause and effect. So clinical researchers would like introduce a drug in a trial and analyze the effect of this intervention on the patients and try to and like try to either like observe the outcome basically on the patient's condition. Okay, let's see if this works. It did not work. Okay, next slide. But in terms of like LLMs and how we can understand them, this method is employed on the computation graph of the model. So you can think of all the operations that Emma went over in the graph or the graphic with the arrows of like inputs flowing through the network as a computation graph where each module is a node dependency that depends on the previous layers. And we can use this causal mediation framework, for example, to try to understand modules that may basically represent bias in this example. So we can hypothesize that this Z module is responsible for storing bias. When we ask the model that the nurse said something and the model assigns a pronoun, a gender pronoun to the nurse subject. So in this first pass, we basically pass the nurse, and the stereotypical prediction is she, while the anti-stereotypical prediction would be he. And we have in parallel another pass where we just give the prompt something that is less ambiguous, like the man said that, where the expected answer is strongly he. So based on our hypotheses, we are going to replace the state of this Z module from the nurse pass to the man pass and see if that has any effect on the final output. And we don't, and so if it does, that would mean that this is like a direct effect towards changing the output of the model. Another way to do this is indirect effect, where we will basically change everything except that module, except the Z module, and see how the prediction changes. And in this case, we see that it does change to Z, to she. So now again, let's go on Workbench and let's play around with some more examples. I'm going to show you some interesting cases in which like the interpretive field has used causal mediation to answer questions about LLM internals. So I'm going to try to share my screen again. All right, let's resume where we left off. So on the side here, if you click on sort of like this graph icon, you can start an activation pattern chart. So activation pattern is just the method that uses this causal mediation framework in the LLM interpretability field. So I'm going to use, so in general, in this method, what we do is we start with a pair of contrastive prompts. So let's say, I love you, you are the most. And a contrastive pair in this case would be, I hate you, you are the most. Let's just use a smaller model so we can see things easily for the sake of this demonstration. And what I'm going to do is I'm going to take the hidden state representation of the last token from the first prompt and patch it, literally replace it in the forward pass of this second prompt, while keeping everything else unchanged. But naturally, because these modules are dependent on each other, the computations of the later layers are going to be modified based on this change. So we run it, and what we're going to receive is a line plot showing the probability values for the expected tokens for both of these prompts. So for the source prompt, it's beautiful, is the prediction that it would normally output, and for the target prompt, it's annoying. And we notice that as we patch this representation at later layers in the model, the top prediction switches from annoying to beautiful. And what we can understand from this result is that after this point, which is roughly layer 10, the model has already, at the last token, processed the information about its context, which contains this like sentiment concept, and it is like it is too late to recover from its original context. And that's why if you patch at like, let's say layer 14, even though hate is literally in the context, it does not change anything. It has already been processed. So with the interface, you can also look at the rank of these predictions. You can look at the probability difference, which if you patch at the earlier layers, the model is sort of like able to recover just like a small scratch. But then if you do at later layers, these mechanisms have already taken place and they're like almost irreversible, unless you do some more surgical operations. You can also choose to look at different other tokens and how they are affected by this change. You can look at the probably difference as well. So earlier there was a question by Jerry about understanding like how does like the location of these concepts and where we see like a change, how does that affect like the last token? So in this setup, we patch from the last token of each prompt, but let's say we wanted instead to patch from love to hate. So just as a reminder, this is, we are seeing here that the probabilities shift from annoying towards beautiful, and that becomes the dominant prediction. If we sort of swap this patch, we're going to see a different trend, that at the earlier layers, it is beautiful that comes up as the top prediction. And then later on, it sort of settles with annoying, which is the original correct prediction. And here's what explains this difference in results. Because we're patching at different positions, we are affecting different parts of this computational graph of the model. And this tells us that if you patch at the later layers, the final token, which is untouched here, it's unmodified or uncorrupted, has already processed the information of the concept of hate. And so changing hate at later layers does nothing to the model. You are corrupting it, but you're not changing its output. And you can even notice that the probability of that token is pretty flat. It's not even changing as you're patching at different layers. So it's very important to keep in mind when you do causal experiments to be aware of like where you're patching. Is it at the later layers? Is it a concept across different contrastive pairs? But the takeaway, regardless of where you patch, is that you're able to localize which parts of the model. In the first example, we saw that like at layers 10, that was where the final token was fetching the concept information. Whereas now that we patch from a concept to another, we see that that representation is enriched just a few layers earlier at this point in the model. I don't know, maybe if anybody, I have a couple more examples I want to share with you, but if anybody thinks they have any questions, they want to jump in and ask, so it can be easier to follow along with the remaining two examples. Can you explain this here, please? I hate you, you are mine. I love you, you are mine. So are you suggesting I just swap the two prompts? I start with I hate you. So I'm reading Krishna's question in the chat.
Yes. So I patched love and hate and also my at the end. So that gave so I wanted to see what if I do a switch twice. That gave a U-shaped rank. So where it is first good and then goes down and then comes up again. So I just wanted to understand the interpretation of what that means.
So is this what you're saying you tried specifically, right? So you patched both of these places?
Yeah, I did a you are my, but yeah, anything of that sort. Because from what I understand, changing anything at the end shouldn't make any difference in the rank because it's the last layer and also the words are the same. So whatever we switched in the early on should make all the difference, but switching at the end should not as much. But probably I'm somewhere drifting off here.
So if I'm understanding correctly, you're saying like that patching at the last layers shouldn't matter as much, is what you're saying?
Yeah, so that means if you remove the last patch, whatever you see should be the same as if you add the patch because it's the same word and the context is exhausted towards the end.
Okay, so yes, so it is the word, right? But these words, throughout the layers, their representations or like vector are enriched and transformed based on their context. They're not just static meaning words. They transform and adapt to the context that they are in. So here, this most is actually very different from this most if you were just to run these two prompts without any cross interventions, right? And we are taking this most, which is a hateful most, a loving most, and we're patching it into the hateful most, and they're different. And that's why you see that that the model basically, because we're patching about these places, it never gets a chance to output annoying. These are probably the two most important tokens for this sort of like sentiment informed prompts that we are processing. And because we're patching both of them into this annoying prompt, it's almost like if we just ran the loving one without any hateful or annoying information. Does that make sense?
Yeah, yeah.
Please ask more questions. Please follow up if this is not making sense.
But could you do, instead of you are the most, and could you change it to you are my and patch the my? Because for my case, when I did the my, it had an overlapping section for the probabilities.
I see. Okay, let's try that.
Oh, I think probably I was.
Did
Sorry,
you
I
use
was
it?
70B instruct. Sorry.
70B struct? Okay, we can try that.
Yeah. So could you explain that overlap is what my question was?
So I don't think I have a clear answer to this one. So I don't want to like say something wrong. It's not like something I like really studied. But so what I sort of like noticed at first is that these two prompts are sort of outputting different things. They're like related. So it's probably the model he's going to say, you are my best friend, whereas the latter model is saying you are my enemy right away. And this discrepancy in like what the next prediction is can basically result in this difference that you are seeing. Where here there's like a big overlap, which really indicates something different than in the previous examples, where it was like no overlap at all when we were patching these two places.
Yeah.
Does that make sense? So researchers in these kind of like causal experiments usually work with very careful templated contrastive pairs where they try to change just one thing, and where the output is usually pre-controlled. You already know what the output is going to be. And because also, I guess as a general note, because we identify that this is usually the how researchers do their experiment with Gwen, we are developing a way so you can like basically evaluate your pairs of prompts before you feed them into causal mediation to make sure that the results you will get are the expected ones. But to come back to your question, what I would read into this is that this is outputting something a bit different than what this prompt is doing compared to the other ones, and that's why we are seeing different results. And it would be I feel like there's more confounding factors here to try to simply explain it.
I have a follow-up question about experimental design.
Mm-hmm.
You had mentioned it being important to have carefully designed pairs of prompts to be able to run this and get the kind of signal that you typically look for here. Do the prompts need to be similar down to, character for character until you get to the contrasting term? So for instance, like different pronouns and prepositions might be appropriate. So if it's like, I live on the moon or I live in Arizona, those two are, if I'm going to make a distinction between Arizona and the moon, they are going to have different prepositions, articles, so on and so forth. Is it important to really get your comparison down to character by character parity until the term in question, or is there some variation that's tolerable in the typical way that you design an experiment like this?
So from my experience and from like working researchers or talking to them, the answer is usually yes and no. And I'll try to answer that. So yes, it does matter, and you should try to be careful with your templating, even down to like some propositions. Because you should also be careful per model, because maybe in some model a proposition actually is split across two tokens instead of just one. And that's why you need to be careful. And the thing that I like about Workbench actually is in practice, you would need to figure out which tokens to patch yourself. But with Workbench, you can just like sort of interactively with the interface patch from one to the other without worrying about the indices or the mismatch. And in practice, how researchers circumvent this this sort of like obstacle is by averaging results over multiple data points. So over multiple pairs, if you average the results, you sort of bypass this difference that could arise from the small templating changes that are due to grammatical structure of like you have to use in versus on.
Great, thank you.
Well, why do you have to mediate between them? Why can't you, aren't both responses potentially, in some, maybe not in the example used, but in some cases, there could be multiple answers, right?
Yes, I think the idea is to look at what that does to the behavior so that we can understand the behavior. Yeah.
Okay, good, really good questions. I hope this like helps everybody understand the method more and like clarify if there's any things that are like still a bit confusing. It definitely it took me more practice and building this thing to fully understand it. So I'm going to show you more examples, and hopefully these things can be even more engaging and like create even more interesting thoughts related to this. So now if I don't know if you're familiar with something called in-context learning, where similar to the first prompt that we started with earlier, models are able to infer tasks in context, and researchers in the space refer to this as in-context learning because you're not explicitly telling the model to do something, and it just figures it out just from you providing a few examples, and it just performs this pattern recognition and ends up predicting the thing you are expecting. So similar to the translation task we started with Logit Lens, I am going to give the model a few examples, which we refer to usually as few shot, of translation from English to Spanish in the first prompt, and then from English to French in the first prompt. So here I'm expecting the model to output sueño for dreams and output fleur for flowers in this prompt. And so again, here we're following a strict template, like the colons and the commas, just to like eliminate any perturbations that may not give us the right signal. And we run it with the patch on the last layer. So we see that the model is outputting the right prefix of the expected token. So again, we're not seeing the full sueño here because of tokenization, but if we let the model predict two tokens, it would have predicted sue and then yo. And the same thing for the English to French prompt. We are seeing the prefix for fleur. And just moving my zoom to the side. So similar results to our first causal mediation experiment. We do see that fleur rises at the top at the beginning, and then sueño, which is like the prediction that this context would basically boost, comes up at the end. But the interesting thing about this example is if we look at the prediction of flowers in Spanish, which its prefix would be flores, it emerges in the middle layers between the prediction of dreams in Spanish and the prediction of flowers in French. So this kind of behavior in the literature is referred to function vectors, where basically the model was able to construct a function that it learned or observed in the context, and it used it on this representation of dreams to perform the task and return sueño. And that function vector is basically developed in these layers. And so if we take the representation from this prompt, which is English to Spanish, into an English to French, at these layers, what we end up doing is switching the function vector from a translation of Spanish one to from a French translation function to a Spanish translation function, while we can preserve the state of the token we are trying to translate. And so we can clearly here see that flowers ends up being predicted in Spanish in these layers. So there's a great paper called Separating Tongue from Thought that was showing that did like a whole like really diligent analysis on this and documenting these kind of like phenomena empirically with a lot of data sets and examples and a lot of languages as well. I see some questions.
What comparisons do you think are productive between something like a function layer and analogical thinking? Like, because the example that you give, right, is actually like back to the nightmare days of standardized tests, where you'd be given an analogy and then you'd have to complete the next analogy. And it feels like this is a sort of series of analogies, and then you think about what. So is this analogical thinking? Do you think it's productive to leverage this kind of thing using analogies based on what you know? Just trying to stretch some of this into an interdisciplinary space a little bit.
Yeah.
Forgive me if it's not quite on the mark here, but that came to mind.
So let me see if I understand the question properly. Are you saying that like by you referring to analogies, are you referring to these like few shot examples that we are passing in context?
Yes.
And so here's where it comes really interesting. So researchers in our field sort of like purposefully use this thing because they're interested in studying this phenomenon. But even if you're not interested in studying the phenomenon itself and you just want to study certain model capability, when you are working with non-instruct models, you do usually want to follow this sort of format because the model is able to understand under the hood the task you want it to do without you explicitly saying it. Because these base models are not very good at task or instruction following. So we do have chat models available on NDIF that you can also access and do the same thing. And those are good at following instruction. You would just select, translate this from Spanish to English or vice versa, and you'd be able to follow because they were fine-tuned to do so. But these base models will usually try to take things literally and not really good at instruction following. And this is a hack for interdisciplinary researchers, basically, to still get the results that they're interested in, even on base models. And it's sometimes even better to do it on the base model because you can study the pure like raw mechanism without like the instruction mechanism being overlaid on top of it.
Yeah, thank you.
Okay. Okay, I'll do another example. So we are going to bring our usual Alice and Bob to this. So the next contrastive pair I'm going to do is again another one with a few examples, although it doesn't follow like the sort of like very base template that we had. This is a bit more like language. And so we're going to say Alice likes dogs, Bob likes cats, Charlie likes mice. We know that Bob likes. The correct prediction here would be cats. And what we're going to do in the contrastive pair, where you don't need to just like switch an entire word, you can also just switch order of entities. and see how the model processes or follows those entities. So here we're going to swap the order of Bob and Alice in the sequence of subjects and objects that we have. And we will also give all of them different objects that they like. So we'll start with Bob likes pizza, Alice likes pancakes, Charlie likes burgers. We know that Bob likes. So let's patch from the last token again to the last one in the target prompt. And we're going to run this, and we're going to observe again the same results. So cats is the right prediction in the source prompt. Pizza is the right prediction in the target prompt. And I would like to emphasize again that these sort of like pairs only work when the model in the first place is able to predict the right thing. So like we know if the model predicted, I don't know, mice in this case, then you should not be working with this pair of example. Maybe the model is not able to solve this task. Maybe this prompt is just weird. So it will not help you see the things you are trying to see or learn. And you should refrain, like you should either use another data set or use a bigger model to do so. So we notice the same sort of like pattern. Pizza at the beginning, and as you patch layer, the mechanism or the happens in the model, and this representation of Bob has been enriched with cats here, and so you're literally patching it, and so it's too late. But let's look at what's happening in this like sort of like middle area. And let's specifically look for the probability of pancakes. And we see that pancakes really emerges in the middle layer. And the reason why I picked pancakes is because it is the same sort of entity of the second subject in this prompt, which was also the same order of Bob in the source prompt. And similar to how in the previous example, we saw that there was a function vector being developed in the intermediate layers that we were able to literally grab from one prompt and insert into the other one while not corrupting fully the output of the model. We are literally able to swap basically mechanisms. Here, this sort of mechanism here is some entity binding where first likes or Bob, the subject, is going to basically get binded to like an order here in the sequence. So in the first prompt, you will basically be binded to this Bob that is here in the second position, whereas in the second prompt, it will bind to the first Bob. But if you patch from this prompt to the other one, it will end up binding to Alice, which is in the second position. And that's how it's able to predict pancakes in these intermediate layers before it actually does predict cats at the end. So these are sort of like the examples I prepared that I wanted to show you, and I'm glad we had a lot of back and forth questions. And what we can do next is basically give some more free exploration time. I would love if you even want to share your screen if you want and show us an example, or if you want to give me a prompt to run and to talk over and try to analyze together. Or if you have any questions. So yeah, so feel free to jump between Logit Lens, activation, patching, and yeah, give us feedback, please, if you see any bugs, any things breaking.
You know, one thing that occurs to me as people do a little bit of exploring, I think that feels like an important project moving forward is to be able to operationalize or at least define what we would call sustainability tasks. So based on kind of understanding a little bit better what some of the operations are that are visible to mechanistic interpretability, what are some tasks that are important to sustainability? Are they question answering and fact finding? Are they certain kinds of calculations or operations that pertain to science or chemistry? But I'm asking them as if this is an or question, right? But it's really just more of an enumerating list, right? But there's like other things that might have to do with place-based reasoning. So how could we better formalize a list of operations that are really relevant to sustainability? And I pasted in the chat just an attempt to see if you could break the analogy or doing a chain of analogies and see if you could break it by doing a not very consistent set of analogies. But it returned just double tilde for each one every time. So I wasn't quite sure. But yeah, sorry, Jose, I see that you have a question. Oh, I get it. You're adding questions to a sustainability research agenda, which is what are the most energy intensive things and which operations can be most easily made more efficient.
Yes, I did not mean to interrupt your flow. It's just that when you mentioned that, it so happens that a very intense discussion around what you might call sustainability circles is can we identify areas that are very energy intensive and why? Conversely, are there obvious things that can be done to intentionally decrease the energy intensity of models? But that's I think it's complementary to what you asked, Michael.
So you're saying we could have a tooltip for kilowatt hours used of electricity every time there was a result for a Logit Lens or the activation patching tool?
Well, that sounds. I actually think there are a lot of colleagues that and students, by the way, who yes, I know it sounds kind of perhaps not realizable, but on the other hand, when we talk about black boxes, and one thing that does seem to be very black boxy like is okay, I get it. It requires electricity. We cannot violate thermodynamics, but how much? How much? And do I have any control in minimizing that or not? So yeah, something like a meter, yeah. But I can see how that would not be easy to do, especially for models that are not open. But anyway.
Interesting. So Michael, going back to the pair of prompts that you pasted in the chat, are you said so? Okay, let me try to run them. And are you saying that you were patching from the last tokens?
I tried patching from a couple different places.
Okay. So let's see. So the model, so the model is basically robust to sort of like the perturbation or attack you did on the prompts, where even though here you have from cold to cold, it's still able to predict the right token. And so that's why you can see that the probability like is pretty like straight and constant overall. There's like some slight variation, but because they both amount to the same final prediction, there isn't like there isn't really any change. So the model is still robust to this.
Yeah, cool. Very interesting.
What if you repeated every word in the first prompt?
Yeah, let's do that. So dog. So the model rightly predicts up in the first one because it's following that. And we are seeing the same pattern basically where it would predict down first here, and as the layers progress, if you patch later on, it will end up flipping to up because this is sort of like the place where that mechanism takes place and refers to its context to make a prediction. So here there isn't like really in the middle, there isn't something really happening because it sort of directly go from up to down without anything taking place in the middle. In the previous example, you can see that like pancakes really takes up a big chunk of the top prediction at these layers.
I copied Jerry's prompt and then added another one. Maybe we could try seeing how that works.
Yeah, I love it. Okay. So in this one, if I remember, we had like a lead-in space because this is actually related to tokenization. So in llama models, and so this is something to be aware of, the numbers are in the vocabulary without any lead-in spaces. And so if you had a prompt, for example, that is normally going to predict a number, and if you don't give it a space after the last token, it's going to first predict that space so that it can predict the number. And so that's why you should, in this case, if you're informed or after trial and error, add a space so that it can correctly predict the number or digit, etc. Okay, so let's try patching from one token to the other. And maybe we need to move up to 70B because I think that was the model that Jerry was using. So I don't know if this is a correct value, the 15 one. Please, sustainability folks, teach us.
It would be interesting to enter a value and then to see what measurement it actually supplies after that value.
It looks like
What?
it's supposed to be 15 parts per billion.
Yeah.
I see. So our values here. So let's move to 70B because we see something more interesting that Jerry was seeing here. Okay, so it's pretty similar, and we see like a really sharp change here in 70B. It almost seems like this maybe mechanism or concept is localized very strongly in a really small section of the model, and everything else almost like stays constant, which is really interesting. And I guess maybe I should talk about some related concepts to this in the literature. So the reason people sometimes like to work with bigger models is not just because they are more capable, but because they can also be more interpretable in the sense that because they are much larger, both in length and width, meaning their dimensional space is bigger than the one for, let's say, Llama 8B, that means they have more dimensions and can assign more unique directions to concepts. And so have more monosemanticity rather than the smaller model that have to basically entangle a lot of concepts in a smaller dimensional space together, which is harder to extract and understand for us, which causes polysemanticity of neurons and activations. And so sometimes these bigger models can allow you to isolate signals and understand concepts much easier. And there's a whole other branch of the field which likes to work on something called SAEs or a sparse autoencoder, which what they'll do, even on these smaller models, they will take these like intermediate residual activations and they will train a network that will project them from this smaller dimensional space into a much larger one. And so further disentangle these concepts with like unique, like almost one-shot directions into the space so that they can study them, isolate them, even use them for controllability on the model, which steering, which is also something we're hoping to add on Workbench. So let me, from Arsen to Led. Let me try. So, okay, this is, I guess, also something practical to show. So arsenic here is tokenized into 2 tokens in this prompt. And usually what the researchers do for causal mediation experiments is they patch from the last token because the last token sees everything before it. And so ik sees arsen, but arsen does not see ik. And so the sort of information of arsen is going to flow into ik, and then it's going to flow into the last token. And so what people do is they patch from the last token. That's where it's going to ultimately contain the full representation of arsenic, whereas arsen may not know that full context. So I'm going to patch from ik to let, which can be a little bit counterintuitive. I'm just patching from IC, but it is going to be enriched with the entire thing before it, which these models are called causal autoregressive models. They're causal because they only see everything that's before it, and they're not affected by the things that are after it. So here again, because we're not patching the last layer, we see the reverse results, where at the early layers, it's predicting 10, and then it switches to 15 at the later layers. I wonder if these values mean anything, the 0 and, I don't know, the 50, the 20s. But I do see the 0 in the middle layers.
Billion.
Good.
And these, where did these other numbers come from?
These were okay, so by default, Workbench is going to gather the probabilities and results for multiple tokens
I got
at a
it. I got it.
time. And but how does it fetch these specific tokens? It will make it really slow and like memory hungry if we fetch the entire vocabulary space and all the probabilities across all these runs. But the heuristic here is, like you can see here, we fetched 17 tokens. And we're going to add functionality so that you can request tokens on demand if there's like some value that we're really looking for that we didn't fetch using our heuristic. But the heuristic is for every patched layer, what are the top 10 tokens that will come up, and we grab their probabilities. And the 17 is a unique set over all of these layers. So over all these layers, over all the top 10 predictions at every patched layer, the unique set of that was just 17 tokens. So there was pretty good consensus over all these tokens, smaller variation in which tokens come up first.
Great. Great.
So, yeah, maybe it would be cool, like Michael was suggesting, to if we could get a prompt where the output is actually the unit for the measurement. But I feel like it would be cooler if we could get two different prompts where the units are different. So now I need help from the sustainability people to think of a second prompt
Our
where it's not going to
toxicology
be.
people. Yeah.
Yeah.
Do we have any environmental engineering or toxicology people? I'm not sure if any are on the call right now. But I'm trying
What
to
else
think of,
other than parts per billion?
yeah. Um,
Um, you could change drinking water to air or something like that, maybe.
could also look at something like radionucleotides. I think those are different units, so we could try radionucleotides, see what happens. Yeah, Jose, that also seems like a good one.
Am I spelling nucleotides correctly?
Radionucleotides, yeah.
Okay. All right, let's try patching from oh, but it will show first, I guess. It will show the digit number first, and then it's going to show the unit. So maybe we can cheat and add in the unit, the number, and then we can let it predict the unit.
It looks like it's 5. Try 5. And it's radionuclides.
Yeah, sorry about that.
I did I just I didn't even know what that was, so
Apparently I don't either.
Emma, like this?
I just texted
There's
it.
no E.
Oh, one word, I see.
Tales from taking a wrong turn down the EPA website.
Yeah, I think it's parts per billion. It's going, instead of the acronym, it's going to write out the entire thing.
Okay.
Still a billion.
We could try this data center. You could patch the data center temperature increase, and then you could also ask about how much water it uses.
We
So not for nothing, I think the radionuclides is now measured primarily by parts per billion.
It's not measured with parts per billion. Okay, interesting.
Model might just not know. It might be like
All right.
But I mean, this is
Let's try to scale it up and see if we get any luck.
yeah, but I mean, it strikes me that this is one sustainability task that is important. Is understanding the proper metrics and standards. So metrics and standards are such a big part of environmental regulation, and that having a full knowledge of environmental regulation right down to what the measurements are and how those relate feels like an important sustainability task, right? If we're to enumerate them as we go, that feels like an important capacity to be able to measure for experts later on.
So is it millions for the radionuclides?
Apparently it is a disintegration per second or a picocurie per liter, or
see.
there's other things for dose assessment. None of them are parts per billion.
I see. So I guess we were biasing it.
Right.
And this just predicted the space, basically. That's what this is. Yep. I think we need to find some solid sustainability tasks and prompt to be able to like get the right information.
Yeah, although this is illuminating already, right? In terms of, it seemed like performance was pretty straightforward when it was parts per billion, but as soon as we introduce a comparison where the units of measurement are not identical, then that's a different story, and that's important to know. Emma, I see what you have down there. Is that a
And also it
maybe?
looks like by connecting the is directly without the space token, it is giving more words, but the moment we add a space, it's then giving a number of sorts as the next token for both this both the batches.
Okay, this is better. We are seeing different metrics.
Yeah.
Emma,
So
are you
our
sure your PhD in neuroscience?
Actually not sure. Are facts always, do they always seem to be localized in the central layers of the network? And are they like consistently localized there? Or does it just depend on the fact? Do you know that?
It does depend on the context, but they are usually, yes, in the middle to like first half of the model. Yes. And even if you can see maybe some facts that are like using that are completely different contexts and they would be localized in the same layer, that doesn't mean that they are following the same circuit or mechanism, because these models have a lot of dimensions, and so they can do things in parallel in those dimensions. There's also a submodule of these layers is the attention module, which is the one that it uses for this like causal understanding of what comes before each token. And that has multiple attention heads that the model usually uses to specialize for different tasks. And so sort of like a follow-up, usually after researchers localize these layers that are like most causally important, they will go and do a more fine-grained activation patching, where instead of patching this like sort of like higher level module output, they will patch the individual smaller module in the big module to sort of like more narrow down even more these are causally relevant components. That's also hopefully comes into Workbench, so you can directly run it. But that is like more computationally expensive because the search space, if you do it over all the layers, but localizing like this first always helps. But if you end up doing over all the layers, it is more computationally expensive because it's a bigger search space, can easily explode. But we have some good optimizations for it.
This is a good, so we're wrapping up basically our interactive session now. Adam, maybe you can demonstrate the export functionality really quick, and then we'll pass it off to Gwen for the reflection portion.
That's right. So it's coming to the Logit Lens tools, but we have it already supported for the calls and mediation tools. And so if you hit the export button and sweet. So the notebook I exported, which I just opened in my IDE right now, is basically like a runnable notebook where the same inputs that you had on your charts and the model that you picked, we were working with 405B instruct in our case, and the data center example is directly embedded into the cells of the notebook and also the chart. So you can, even with its interactivity. And the idea behind this export mechanism that we developed with Gwen and Emma is if you want to continue your research workflow with your own data, something more intensive, or you want to do more fine-grained experiments, then we want you sort of to preserve the state that you were working with on Workbench and transition smoothly without having to recompute things that are not necessary, without having to figure out how to install the library or anything. So we have currently, this is under this like insightful package, which is like really convenient. It works with any model. There is open source on Hugging Face, and either locally, if you set remote equals false, you can use your own models, or for the models hosted on NDIF equals true, and you can access all the models on NDIF and run this experiment on more data. You can loop over this function. We have also more tools coming to it. So I'm gonna give it back now to Emma and Gwen to sort of like wrap up this interactive demo. I hope I was able to teach you something. I was able to introduce you to some good and interesting sort of like methods in interpretability, and would love to hear your feedback about Workbench. I'd love to hear if you're interested in using it for teaching some class or even doing experiments. So yeah, please reach out if anything like that seems interesting to you.
All good?
Yeah, I think so.
Okay, cool.
Yeah, so we're running a little tight on time, but we wanted to give you guys an idea of where you can go next from kind of like the tip of the iceberg, which is what we were looking at today. So Adam demonstrated the export feature, allowing you to get into a notebook and then use Insight or Interp to expand your experiment. Because as I think we very briefly mentioned, most of the time you'd actually be working with like a full corpus of prompts, and you want to average your results over many experiments. And so eventually transitioning away from the sort of like initial intuition building tools like Workbench and into something that's actually supported programmatically is necessary. And so we have tooling built around that. I don't think I have the next slide though, Emma, if you want to. And then also wanted to share some research inspiration, some projects that other people have already completed, in like other fields that are not computer science using the NDIF tools. So you can get an idea of like maybe how this can be used. So this first example is from psychology. And as you can see, like this team used interpretability methods to study how a language model expresses emotions. And they basically found that as the models get larger, emotional representations become more hierarchical, which, because this was a team of like domain experts in psychology, they were able to tie these conclusions into their understanding of human cognition as this mirrors our like understanding of what structures exist with how humans understand emotion. Um, this project is from medicine, and so this team was actually using activation patching, which is exactly what Adam just showed, to find where inside a language model, possibly used in a clinical setting, demographic information like gender was being encoded and how it was influencing outputs. So this kind of example here is showing why a different recommendation might be given for a patient named Sarah versus a patient named John. And the idea is like that they did this many times with many examples, and now they have an idea of where in the network that divergence might be happening. So for then controlling your model later, or for doing an audit of bias in healthcare, this information might be useful. And our third and final example is from biology. And this was for a more for a subset of models that are protein language models, and they were looking to see if they could discover interpretable features corresponding to specific biological structures, which they were able to discover these biological structures. And this experiment is cool because they were able to do this all computationally and didn't need to use a lab or anything. So hopefully these give you some ideas of like how NDIF can be used in different directions. And so we have an open Q&A, and then after that we do have like a brief survey that we're hoping everyone, if you would like give it a fill out just for feedback on Workbench, on the workshop. Yeah, and thank you so much for coming.
Yeah, thank you. I have a quick question about the emotions paper. Can you just say very briefly what the basic idea there was of that paper? Because it looked like they were mapping out the relationships among concepts. Could you say just a little bit more about NDIF and its role in that kind of research? Because I feel like mapping the model representation of different concepts could be a very powerful like paradigm for the sustainability space.
Yeah. Let me actually just pull that paper up because it was pretty cool. Emergence.
So while Emma does that, if I can like chime in on this, so this is one of my favorite works that I would like refer to in terms of like an NDIF success, and the reason for that is to really find the really complex results that they did was really only possible to do on for the really large model that we host, which is 4 or 5B. Like there's some hierarchies of these emotions that they could only discover on the really large models, which is like really cool. And that's like really part of our mission to like enable this like really ambitious research projects on models that most individual labs would not be able to like easily host, just because not only because of like GPU compute limitations, but also because of the engineering it takes to deploy and host these models permanently and manage them and all the things that it takes.
Yes.
But in terms of like the actual sort of like experimental setup that they did, they basically just grabbed a bunch of like activations on these like sentiments from like prompt context and they then did like some analysis on those activations that they were able to grab and do things like PCA or like UMaps to like sort of like hierarchically like define which to be able to like rank the components that are like most important for these different sentiments and how they differ from the other sentiments.
And I
Yeah.
think Emma can probably speak more on this, but I believe this team was also part of the pilot program with NDIF, where like provided like resources and support for experiments early on.
Yes. Yeah. So it's pretty cool because it was a interdisciplinary team with some computer scientists, researchers, some psychologists, and their idea was to take this concept of emotion wheels that are used in psychology, and then have prompts where the language model takes classifies the emotion exhibited in that prompt. And then from there, there are like upper level classifications like sadness, joy, and love, but there are a lot of much more detailed emotional classifications that humans are able to exhibit. And humans have an understanding that love may be an upper level of something like adoration and compassion. Um, and they found that a small language model like GPT-2 was not able to capture this complexity of these hierarchies. But as the language models increased in size, they were able to better capture the emotion wheel capabilities of humans. And then they also went into some interesting stuff about racial bias in these emotions. Like, for example, if the prompt was about a person of color, the language model might be more likely to classify it as anger instead of as fear or something like that. So it was actually really interesting to also show how they might have this complex hierarchy of emotions, but it can also lead to bias in their through the bias in the model.
Terrific. Thank you. And could you say again what the title of the paper was? Because
Yes. It is, let me zoom out. Emergence of hierarchical emotion organization in large language models.
okay, yeah, brilliant. Thank you so much.
Yes.